Let us talk about complex analysis. Complex analysis is traditionally known as the theory of functions of a complex variable. It is a branch of mathematical analysis that investigates functions of complex numbers. It is useful in many branches of mathematics including algebraic geometry, number theory, analytic combinatorics, applied mathematics, as well as in physics. Complex numbers. The real number system. The number system as we know it today is a result of gradual development as indicated in the following lists. Natural numbers, also called positive integers, were first used in counting. If a and b are natural numbers, then sum of a and b and product of a and b are also natural numbers. Second is the negative integers and zero, denoted by -1, -2, -3, and so on, and 0 respectively, permit solutions on equations such as x plus b equals a, where a and b are natural numbers. This leads to the operation of subtraction or inverse of addition, and we write x is equal to a times b. Third is the rational numbers. Permit solutions of equations such as bx equals a for all integers a and b where b is not equal to 0. This leads to the operation of division or inverse multiplication, and we write x is equal to a over b, where a is the numerator and b is the denominator. Irrational numbers. Irrational numbers such as square root of 2 and pi are numbers that cannot be expressed as a over b, where a and b are integers and b is not equal to 0. Let's proceed to the complex function. Complex function is one in which the independent variable and the dependent variable are both complex numbers. More precisely, a complex function is a function whose domain and range are subsets of the complex plane. For any complex function, both the independent variable and the dependent variable may be separated into real and imaginary parts, where z is equal to x plus iy and w is equal to the function of z. In other words, the components of function is a function of z. Absolute value. The absolute value or modulus of a complex number a plus bi is defined as the absolute value of a plus b equal to the square root of a squared plus b squared. For example, find the absolute value of -4 plus 2i. We are going to use the formula absolute value a plus bi equal to the square root of a squared plus b squared, where a is equal to -4 and b is equal to 2. So we are going to substitute the values. And we come up with the final answer 2 square root of 5. If z sub 1, z sub 2, z sub 3, and so on, z sub n are complex numbers, the following properties hold. The following. Graphical representation of complex numbers. Suppose real scales are chosen on two mutually perpendicular axes, x and y, as in figure 1 of 2. We can locate any point in the plane determined by these lines by the ordered pair of real numbers, called rectangular coordinates of the point. Examples of the location of such points are indicated by P, Q, R, S, and T in figure 1 of 2. Since a complex number x plus iy can be considered as an ordered pair of real numbers, we can represent such numbers by points in an xy plane called the complex plane or Argand diagram. The complex number represented by p, for example, could then be read as either 3, 4, or 3 plus 4i. To each complex number, there corresponds one and only one point in the plane. And conversely, to each point in the plane, there corresponds one and only one complex number. Because of this, we often refer to the complex number z as the point z. Sometimes we refer to the x and y axis as the real and imaginary axis, respectively, and to the complex plane as the z-plane. The distance between 2 points, z sub 1 is equal to x sub 1 plus iy sub 1 in the complete plane is given by polar form of complex numbers. Let P be a point in the complex plane corresponding to the complex number x, y, or x plus iy. Then we see from figure 1 of 3 that x is equal to r cosine theta and y is equal to r sine theta, where r is equal to the square root of x squared plus y squared, or the absolute value x plus iy, is called the modulus or absolute value of z equal to x plus iy. Theta, called the amplitude or argument of z equals to x plus iy, is the angle that line OP makes with the positive x-axis. It follows that z equals to x plus iy, or r multiplied to cosine theta plus I sine theta, which is called the polar form of the complex number, and r and theta are called polar coordinates. It is sometimes convenient to write the abbreviation CIS theta for cosine theta plus I sine theta. For example, express 1 plus 2i in polar form. Draw the figure. So we are going to use the solution z equal to 1 plus 2i, where x is equal to 1 and y is equal to 2. So first step is to find r, or the absolute value of z, which is equal to the square root of x squared plus y squared. So let's substitute the value. So we have the answer, r is equal to square root of 5. Step 2. Find theta. From figure 1 of 3, we can see that the location of our angle theta. Then, we can say that tangent theta is equal to y over x, where theta is equal to the inverse tangent multiplied to y over x. So we are going to substitute the values. So our theta is now equal to 63.43 degrees approximately. Step 3. Use the polar formula. Step 4. Draw the graph. Roots of complex numbers. A number w is called an nth root of a complex number z. If w is raised to the power of n equals z, and we write w is equal to z raised to the power of 1 over n. From the Moivre's theorem, we can show that if n is a positive, then this is the formula. For example, find the roots of z raised to the power of 4 equal to negative 16. Draw the graph, where r is equal to 16, theta is equal to pi, and n is equal to 4. So here is the solution. Since n is equal to 4, this means that we have 4 solutions to the problem. First, let k be equal to 0. So the final answer is square root of 2 plus square root of 2i. Next is let k equal to 1? So the answer is negative square root of 2 plus square root of 2i. Next is let k be equal to 2. So the answer is negative square root of 2 minus square root of 2i. And next is let k be equal to 3. So our answer is square root of 2 minus square root of 2i.
So here's how are we going to graph that. Thank you for listening. Hope you'd enjoyed.